Hello everyone, welcome to my talk. Today I'm going to introduce to you some very interesting random matrix inequalities and their applications in randomized algorithms. In the title, there's something called matrix anti-concentration inequality here. And the concentration inequality is an inequality that bounds the deviation of the random variable from its expected value. One of such examples is the law of large numbers. Suppose that x1 till xn are independent random variables with finite variance and zero expectation. Then by Chebyshev inequality, with probability at most 1 over epsilon squared, the sum of the random variables is at least epsilon times square root of n. And the anti-concentration inequality is a reversed form of a concentration inequality, as usual. And it lower bounds the derivation of a random variable from any given deterministic value. The central limit theorem, in many cases, can give a concentration bound and an anti-concentration bound at the same time. However, this is not always this case. Take the Littlewood-Alford theorem example. Let xi's be independent Bernoulli 1/2 random variables and the ai's be deterministic real numbers with a1 till an being at least 1. Then with probability at most log n over square root of n, the norm of the linear combination is at most 1. In the case 1 ai, they all have an upper bound of a constant. Then we can use the central limit theorem to give an upper bound and lower bound on probability at the same time. However, in this statement, there's no upper bound for ai's. And as a result, the linear combination here can be very different from a Gaussian random variable. And in this case, we only have an anti-concentration inequality without having any concentration inequality. There are many high-dimensional analogs of this Littlewood-Alford theorem, but today we are considering a matrix version of this theorem, which is so called the matrix anti-concentration inequality. In this framework, let's xi to be independent random variables, and let's mi be deterministic matrices. And we consider under which condition can we have a polynomial lower bound on the least single value of the linear combination. And remember that the least single value of a matrix is just the norm of the inverse of the matrix. And before we are considering the least single value, we consider a simpler case. Under which condition can some linear combination given the mi's be non-singular? And fortunately, there's all the results in linear algebra that answers this question. It's saying if all linear combinations are singular, then there exists two unit vectors, x and y, such that x transpose times m times y is always 0 for any matrix M in that linear space. This theorem is not well known in the random matrix community. However, it's very important in our study. Our first result is the Gaussian case. Suppose that the GIs are ID Gaussian and the MIs are deterministic. In this case, we only need to assume a global small ball probability bound as follows to derive a polynomial lower bound on the least singular value. And the global small ball probability bound is simply a probabilistic and quantitative version of the condition described in Fender's theorem. Not that except for the epsilon alpha and the m here, we also have an S here. The S represents the norm of the random matrix. And as we know, the norm of a random matrix is always easier to bound than the norm of the inverse of the matrix. And the idea to prove this theorem is to take an independent copy of the random matrix M with jointly Gaussian entries. Let this independent copy be in M prime, and consider another independent random variable U. And then, because it's jointly Gaussian, M plus U times M prime has something to do with M. They have similar probability distributions with some algebraic relations. And from that, we can use Markov's inequality to bound the probability of probability that the matrix M has a small singular value. Our second result is for independent random matrices M0 till Mn. Remember that in the previous slide, the MIs are deterministic matrices. However, here they are independent random. And the global small ball probability looks like the same or similar. What is different here is that we have to have an additional assumption on the lower bound of n. The n is at least m over beta times some log factor. And at some extent, this lower bound on n is necessary. Suppose that n equals to 1 and m0 also equals to m0 equals to 0, and let m1 be a rank 1 matrix. If m1 can be random, then the rank 1 matrix can still fulfill the global small ball probability bound. However, the m here is of rank at most 1. So that the least singular value of m is 0, and there's no way to have a polynomial lower bound on the least singular value. This is the difference between random matrices and the deterministic case. The way to prove this result from our previous results is variation of the epsilon net theorem. Let the small ball probability bound define several learning concepts of the matrix. Then by sampling those matrices independently, they should form a so-called epsilon net. And the VC dimension defined by those small ball probability would be at most linear in M by Warren's bound, because it's defined by inequalities by low dimensional polynomials, low degree polynomials. Okay, so let's go back to the motivation of our research, the starting point of our research. One day last year, our chief scientist in the company saw Peng and Paula's results in a social media. Their result is saying that if we have a sparse matrix A and a vector B, we want to solve the sparse linear system AX equal to B, then this system can be solved faster than doing matrix multiplication in the dense case. And at that time, I was doing random matrix theory and their applications. Then I read Peng and Van Paula's paper, and the end of their paper, they are saying they have some problems in random matrix theory. They proposed the matrix anti-concentration inequality there. And that's why I started working on this. And for the sparse linear system solver, the framework is that we have a n by n real matrix with condition number polynomial of n. And we want to solve the linear system up to accuracy 1 over a polynomial of n. And that's we measure the bit complexity. The Krylov subspace method is as follows. The definition of a Krylov subspace, given n by n matrix A and an n-dimensional vector B, it is the linear span of B, A times B, A squared times B till A to the R minus 1 power times B. And the usual way to use the Krylov method is to minimize AX minus B in the Krylov subspace. And this can be done iteratively and efficiently, especially when A is sparse, then we take B to be sparse, and every matrix vector multiplication would be performed efficiently. In practice and some other theoretical analysis, we take the number of iteration R to be square root of the conditional number. However, in our case, the condition number is large compared to n. It's a polynomial of n. So we consider the full Krylov space instead when R equals to n. But there's a problem on the Krylov subspace matrix is that the least singular value of that matrix is quite small. Suppose that A has eigenvalues 1, 2, 3, then A to the kth power has eigenvalues 1, 2 to the kth power, and 3 to the kth power, and the eigenvectors stays the same. That means the many columns in this Krylov space matrix are close to some low dimensional subspace of the n space here. That makes the least singular value small. And the best we can expect is that we want the least singular value to be exponent to the exp of minus n times some log factors. To improve on the Krylov method, people also consider the block Krylov space method. Instead of taking just one vector b and multiply by many a's, people consider k vectors in the initial step, in the initial step, and multiply by a at most m minus 1 times. We also consider the case when the subspace is a Hom space, km equals to n. Then the least singular value of the block Krylov space matrix can be exp of minus m times log factors at best. By using block Krylov space matrix E, G, G, S, and V, they designed the algorithm to find the inverse matrix over a finite field efficiently. Then in 2020, Peng and Vampala designed the algorithm over the real field. However, they are working on the solving linear system instead of computing inverse matrix, and the complexity is a little bit worse than the original one. Our work is building on Peng and Vampala's work that solves the linear system over real field in a complexity which equals to the complexity of the EGG, S, and V in the finite field case. And our improvement is on the random matrix inequalities. It's saying that we can take sparse Gaussian vectors as those BIs, and the density is m over n times log factors. Then the Krylov space matrix here has the least singular value exp of minus m times log factors. Compared to the previous work, we improved on the sparsity of the initial matrix the sparsity of the sparse Gaussian matrix, so that the matrix vector multiplication would be faster. It's very exciting to see that the random matrix theory can be used to improve the worst case complexity of some important algorithm, other than, say, smooth the complexity of some algorithms. The matrix anti-constitution is also important in compare sensing and high-dimensional statistics. In compare sensing, which is a concept introduced about 20 years ago, there's a famous property of the measurement matrix, which is called the RIP, the restricted isometry property. That is basically saying if we take a rectangular shape submatrix, then call it A, then A transpose times A is close to the identity matrix. If it's close enough, then it gives an anti-concentration bound and a concentration bound at the same time. However, people then find that they can relax this condition so that we only need to guarantee an anti-concentration bound without concentration. In Olivia's result, this assumption on the moment is strictly stronger than the small ball probability assumption. And in Liu and Mendelssohn's result, they are working on rank 1 positive semi-definite matrices, and they use the small ball probability bound. And there's some string on the lower bound of the n is that n is at least m over beta squared. We can improve their results so that we can deal with positive semi-definite random matrices. And the assumption is the small ball probability bound. And also the lower bound of n is m over beta times the log factor. Okay, this is the end of my talk. Thank you very much.